Exercise 16. Suppose that z equals f of xy equals 0.8x plus 0.5y, and the maximum value of z is sought. Both the graphs of f and its domain, feasible region, are provided. Working manually, calculate the maximum value of z. Okay, this problem was discussed earlier, at least as far as whether or not it's a linear programming problem. We have decided yes it is. Just a brief review of how we know that. Okay, first of all, we have optimization going on because we're seeking a maximum value of z. The function is linear with this formulation here, 0.8x plus 0.5y. It's a linear function. And now let's look at how the domain is. The domain, we have this graph here of R. Here's a sort of zoomed in graph of R with some details. And from this, one thing we notice is that it's a convex region, and the boundaries are all solid lines. So that means this could be described by a set of linear inequalities, each of which would be either a greater than or equal to or less than or equal to type. So that's one of the three types of constraints you need to be a linear programming problem. The third one would be in an equals to case. You can have that too, but we don't have that here. Alright, so since it's a linear programming problem, we know that the optimum value, by the way, we also see that this feasible set here is bounded. So you could draw a circle around it and enclose it. That's bounded. And it is non-empty, of course. So this means that z will have a maximum value, and the theorem says it will occur at a vertex. So the basic strategy here will be to compute the value of z at each vertex and just identify the largest value. Okay, so a table is in order. Okay, the table will have a vertex listed here, and z equal to 0.8x plus 0.5y here. Okay, let's perhaps start here. Three vertices, we'll just put them all in the table to begin. So 3.5, 3.2. We'll go counterclockwise. 3.5, 2, 4, 1, 3, 1.52. Okay. Alright, here we go. Got to do here 0.8 times 3.5 plus 0.5 times 3.2. Okay, that's half of 3.2. It's 1.6. And what about that? 0.8. Multiplying by 0.8, you can think of subtract 20% of the number. Another way to do that. And that means 0.35 is 10%. 0.7 is 20%. So 3.5 minus 0.7. 2.8. Okay, 2.8 and 1.6. 3.8, 4.4. Okay. Next vertex, 0.8 times 3, 2.4, plus 0.5 times that, half of 3.5, 1.75. Let's add these guys up here. Let's see, we'd have 5, 7 and 4 be 11, carry the 1, 4.15. Okay, 2, 4. 0.8 times 2 is 1.6, plus 0.5 of 4 is 2. Sum together, 3.6. Next vertex, 0.88 times 1 is just 0.8, plus 0.5 times 3, it's 1.5. This sums to 2.3. Okay, last vertex, 0.8 times 1.5. Okay, we could subtract 20%, and that would be 0.15. 0.30 is 20%, so 1.2. And plus 0.5 of 2, 1. we're up to a total of 2.2. Okay, let's look over the numbers here. We are seeking the maximum value. Okay, 4.4, this is it here. So, right here, the source of our conclusion, we could write the maximum value of z is 4.4. That actually answers the question as asked. I like to add in another detail. This occurs at x, y equaling 3.5, 3.2. The big conclusion. The only way to really check anything here is to just redo the arithmetic one more time, make sure these numbers are okay. And otherwise, this looks like it's it. Exercise 18. Consider the following problem. Determine the minimum value of z, where z equals x minus 2y, subject to 3x minus 14y greater than or equal to negative 67, 2x plus 4y less than or equal to 112, x plus 2y greater than or equal to 6, and 11x plus 2y greater than or equal to 21. Part A. Is this a linear programming problem? Explain the basis of your conclusion. Alright, we look this over and we see this problem concerns finding a minimum value of this z here. Okay, that's an optimization question. That's what we need to see for a linear programming problem. And here's this formulation of z. Z equals x minus 2y. Alright, z is then a linear function. So we've got that aspect of linear programming in order. Subject to, now these inequalities here are all controlling the domain, restricting the domain. Take a look at these inequalities. A linear inequality here, a linear one here, and a linear one there as well. All four linear inequalities, and they are of the permissible types in linear programming, namely either a greater than or equal to, a less than or equal to, and you can also have equals to, but we don't happen to have that here. But all four of these inequalities satisfy that condition as well. Okay, let's write down the answer to part A. Okay, here's our conclusion written down. Yes, it concerns optimization of a linear function value. The domain is defined by a system of linear constraints, each of which is one of less than or equals to, or greater than or equals to. Alright, let's move on to part B now. If this is a linear programming problem, then solve it manually. Alright, let's get started on this. We have already decided it's a linear programming problem. Okay, so what we need to do here would be to graph the domain and find all the vertices. Now, with this domain defined by the system of linear inequalities, we'll take them on one at a time. It'll be a matter of graph the boundary line and then shade the correct side of the line to get the half plane. Then get the intersection of all four of these half planes to finish out. Alright, now what kind of coordinate system will be best for this? If we start looking these over and maybe thinking about intercepts, you know, there's actually quite a bit to sort of think about there. Not to mention the fact that you need to consider the intersection of four of these half planes. We really don't have too much of an idea what to expect. There's just too much going on here. We can just start with guessing with some sort of coordinate system that might work. Maybe we do something simple and perhaps favor the first quadrant, since it does seem linear programming problems tend to have their domains mostly in or entirely in quadrant 1. So let's get started. Okay, labeling the axes. Scaling, 1 per tick mark, let's say. Well, is that a good idea? Maybe we go 2 per tick mark to make sure we get some larger numbers available here. Alright, 2, 4, 6, 8. 2, 4, 6, 8, 10, 12. Negative 4, negative 8, negative 4. Okay. Well, let's take these on one at a time. Let's deal with this first inequality. Let's get its boundary line. We'll call that L1 perhaps, in organizing our solution. So the boundary line is graphing the corresponding equality, 3x minus 14y equaling negative 67. Okay, if we were to let y equal 0, x would be, okay, like negative 21 and then some. Okay, that's too inconvenient for our graph. If we let x equal 0, okay, this might be a graphable point, so let x equal 0, and then this would give us y equaling negative 67 over negative 14. Let's simplify that. First, it's positive, negative over negative. Secondly, let's take multiples of 14 here. 14, 28, 42, 56. Okay, so let's see, 56. That would leave 11 behind. So this is actually 4 and 11/14. Writing it that way helps us figure out what to do with this. Okay, there's an intercept. Let's make blue, light blue, the color coordinates code for this first region here, and a y-coordinate 4 and 11/14. So that's what, about 4.7 or so. Okay, so here's 4. There's 5. About there. Now, another point. The x-intercept is too inconvenient. So what else could we do? Let's see. Maybe we let y be some other number and get x panned out from that. Let's see. We want to make the y here something so that 14 times it is going to add to this negative 67 and give us a 3x equals a somewhat small number so that it's a graphable point. Maybe y equal to 3. Okay, let's try that. Okay, if we do that, this gives us 3x equaling to, let's see, negative 67 plus 14 by 3, 42. Okay, let's see, and that would become 52, 62, 67. Okay, that's 25 with a negative sign. So then that would give us x equals to negative 25 over 3, which is what, negative 8 and 1/3. Okay, let's we can graph that point. That fits on our coordinate system. Alright, let's go here to negative 8 1/3. Remember, there's 9, so 8 1/3 is up in there. To have y be 3, that would be 1.5 centimeters in our case. About there. Okay, there's our 2 points for this boundary line. Sketching it in the light blue. Label its equation here, the boundary line. This is 3x minus 14y equaling negative 67. Now, this is an inequality. Which side of the line to shade? I like to substitute 0, 0 in here and use that as a test point. So if we put 0, 0 into this original inequality, that would be 0 greater than negative 67, which is a true statement. So we know to be shading 0, 0 side of the line. Now, because this is a system, I'm just very lightly shading here to keep track of matters. I need to get the intersection of all 4 half planes in the end, so this just reminds me where to start here. Let's now go to the next inequality and work on its boundary line. Let's call that L2. And that is the corresponding equality of this 27x plus 4y equaling 1112. Alright, let's see. If we let x be 0, we would have a very large number that will not conveniently graph. If we let y be 0, okay, we might be having something there. Let y equals 0. And this would give us x equal to 112 over 27. Let's see, multiples of 27. 4 times 27. 108. Okay, so this becomes 4 and 108. That's 4 left over. 4 and 4, 27ths. Okay, 4 27ths. A little more than 3 27ths, which would be 1/9. Okay, and this is maybe 4.2 or something like that. Alright, so we go here. We're going to go color red for this one. Get the legend going here. And we have y0, x being 4, about 4.2. Okay, there's 4, there's 5, about there. Alright, now we need another point. The other intercept is inconvenient. Let's see. What about letting x be something like perhaps, let's see, what if we did 2? Would that be a graphable point? Let's try it out. Let x equals 2. Alright, so that gives us 54 here. So this means that we'd have y equaling, or rather 4y equaling 112 minus 2 by 27, 54. Okay, so what do we get for that? We get 8, and then it's 58. Okay, and then that leaves us with y equaling 58 over 4. Let's see, that cancels a factor of 2 there. That would give us 29 over 2. Okay, let's see, how big's that? That's almost 15. That's 14 and a half. I think we can get that to fit on our graph. Have to kind of extend ourselves a little bit, but it'll work. Alright, so this point again is 2 for x and 14 and a half for the y. Alright, well there's 14 up here. A 2 for x would be 1 centimeter over. Okay, got that point there. There's our boundary line. Let's label its equation, perhaps up here. This would be 27x plus 4y equaling to 112. Now, which side of the line gets the shading for this inequality? Testing 0, 0 into the original inequality here. If we put 0, 0 in here, we'd have 0 less than 112. That's a true statement. So it's 0, 0 side of the line that gets the shading. Now, already start thinking about intersecting. It looks like so far we're in here for the region. Okay, time to go to the third inequality up here. Alright, let's get our boundary line going. We'll call this boundary line L3. And what about that? We have to consider the corresponding equality of this inequality. X plus 2y equals 6. Okay, this one's got some nice easy intercepts we can just do mentally here. Let's get those going. If y is 0, x is 6. Okay, right there. If x is 0, 2y is 6, y is 3. Right there. Okay, let's graph that line, boundary line. Okay, let's label its equation. This is x plus 2y equals 6. Now, what about the side of the line to be shading in this case? Testing 0, 0 into the inequality here, put 0, 0 here, you'd have 0 greater than or equal to 6. Well, that's false. So it's the other side of the line that gets the shading. Not here, up here. Now, considering the intersection idea, it looks like we're now reduced to this triangular region in here so far. And we still have another inequality to deal with. Okay, this one here. Let's get the boundary line, call it L4, and that's a matter of graphing 11x plus 2y equaling 21. Okay, maybe we can get the intercepts here pretty easily. Let's see, first of all, to be consistent getting our legend, this was a green, and now let's go to a purple for the L4. For its intercepts, if we let x be 0, y would be 21 over 2. It's 10.5. Okay, graphable. 8, 10. There's 11 right there. Okay, now if we let y be 0, x is 21 over 11. That's very close to 22 over 11. It's very close to 2. Alright, so a point here, just a micrometer to the left of 2, and then graph this boundary line. Okay, let's label its equation. This is 11x plus 2y equals 21. Now, which side of the line gets the shading here? Okay, substitute 0, 0 into this inequality, see whether it's true or false. It would give us 0 greater than or equal to 21. That's false. So it's not 0, 0 side of the line, not over here, it's over here. So now the part of the triangle is now reduced to, in here, a quadrilateral, and now we are ready to actually shade our final region here. Let's see. Okay, let's label this as R. R is going to be the region which is the domain or feasible region for this problem. Now the next issue is vertices. Okay, looks like we've got 4 vertices here. Let's see, we got one here, one here, one here, one there. Okay, we need to get all of these. So let's get started here. This first one is a matter of the intersection of the red line and the blue line. Alright, we've got our equations labeled, so this will be a pretty straightforward process to set it up. Okay, let's start our work here. Vertex calculations. Alright, we said the red line, that's 27 plus 4y equaling 112, and the light blue line, that's 3x minus 14y equaling negative 67. Okay, let's see, what could we do here to set up our elimination? Maybe, okay, we could work through this equation. minus 9 of these will eliminate the x's right away. Okay, let's get going here. So 27 minus 9 of these, no x's left over. Now 4y, subtract 9 of these, that means add 9 times 14. Okay, let's see, 10 times 14 is 140, so 9 of it would be 126. Okay, so this will give us 126, and that 4 is 130. Y equaling, okay, subtracting 9 times negative 67 is adding 9 times 67. So let's see, 670 is 10 of it, and so 603 would be 9 of it. 603 and 112. We're up to 517. Okay, 715. Okay, we divide both sides by 130. Y equals 715 over 130. Okay, a factor of 5 obviously cancels right away. What's that leave behind? Let's see, 5 goes into this 1 times, 21 left over. Goes in 4 times, 15 left over, 3. Okay, down here 5 goes into this. You can just divide by 10 and then double the result. Divide by 10 is 13. Double it, 26. Okay, what about this fraction here? This is 2 by 13. Oh, 13 divides 143 evenly too. Okay, so this is going to, let's see, 13 goes into that once, and 1, 3 left over, 1. Okay, and divide by 2. Alright, great. So we got that. Now the corresponding x we could pull off from the second equation. Okay, 3x would equal negative 67. Now we have to add 14y plus 14 times 11 over 2. Cancel, cancel. 7, that's 77. Alright, 77 and negative 67, that's positive 10. So it looks like x will equal 10 thirds. Oh, by the way, something I should have done even right here is looked for some graphic consistency before going further in this question. Now, how about this y at 11 halves, 5.5? Let's look at this point. Okay, here's 4, there's 5, 5.5. Yeah, very reasonable for the y coordinate. How about this x coordinate at 10 thirds? Look at for graphic consistency. 10 thirds, it's like 3 1/3. Alright, we're up here. 2, 4, a little over there. Yeah, that's reasonable for graphic approximation. Okay, so we can somewhat confidently label this vertex here as 10 thirds, 11 halves. Go into another vertex. Let's say this here, green line and red line. Green line, red line. Okay, red line, 27x plus 4y equaling 112. Green line, x plus 2y equaling 6. By the way, let me put some bullets here so that it's organized. I want your solutions to be kind of clear. Alright, let's see, what have we got here? We've got a chance to use a nice elimination method. Looks like the first equation minus 2 of the second will eliminate the y's. Let's try it. 27 minus 2 of these x's. 25x. The y is eliminated. 112 minus, well, 12. Okay, 100. Oh, that leaves us with x equals to 4. 100 divided by 25. And then the corresponding y, we can recycle this first equation. Looks like we'd have, let's see, 2y equals 6 minus 4 equals 2. Y equals 1. Is that consistent with the graph when we go to that point? 4, 1. 4, 1 looks good as well. Okay. Alright, let's go to this point here. This is the green line and the purple line intersecting. Alright, so the purple line's equation was 11x plus 2y equaling 21. Let's put a bullet here so we notice that we're starting a new calculation. And the green line, that was the x plus 2y equals 6. Oh, okay, this is already prepared for elimination. First equation minus the second. Let's see, this is 10x here. The y's eliminate. 21 minus 6. Okay, that's 15. Looks like x becomes 15 over 10, better known as 3 halves. Is that graphically consistent? Here, yeah, there's 2. We're to the left of 2. That looks pretty good. Alright, let's get the corresponding y. We have 2y equaling to 6 minus 3 halves, which would be known as 12 minus 3 9/2. So then this gives us y equaling 9/4. What do we think about that graphically? 9/4, that's like a 2 1/4. Okay, there's 2, we're above 2. Yeah, this looks pretty good. Okay, so right in here, got a vertex. It is 3 halves, 9/4. Okay, almost there. One more to work with. Here we are intersecting the light blue line and the purple line. Okay, that light blue line, that's 3x minus 14y equaling negative 67. The purple line, 11x and 2y equaling 21. Okay, alright, it wouldn't be too hard to get the y's to eliminate. We could add 7 of these to the first equation. Okay, here we go. 3x, 7 of these is 77 x's, so that adds up to 80x. The y is eliminated. Now we need to add 7 times 21. Okay, let's see, that is 147. Okay, so we have 147 and 67 with the opposite sign, so we subtract the 67, we would end up with an 80 there. And let's see, what about that sign? That was this one. Add 7 of these, that's positive 80. Oh, okay, so that would leave us with x equal to 1. Does that look graphically consistent? This point, okay, x about 1 looks okay. Alright, let's force out the y, recycle the second equation. 2y could equal 21 minus 11 times 1, known as 10 then, gives us a y equal to 5. Does that look consistent with the graph? Yeah, there's 4 and there's 5 right in between. This actually looks pretty good. So 1, 5, vertex there. Okay, we have got all our vertices. Now, in the spirit of linear programming, we know we should be evaluating the z function value at each vertex and choose, in this case, the minimum. Okay, so here we go. We set up a little table. Vertex and z equaling x minus 2y. Alright, let's see. Let's round up our vertices. We can look at the graph and do this. We can have 4, 1. We could have 3 halves, 9/4. Could have 1, 5. And 10 thirds, 11 halves. Alright, starting here, x minus 2y. That's 4 minus 2, known as 2. Okay, here, x minus 2y. 3 halves minus 2 times 9/4, okay, 9 halves. And that will give us, let's see, a negative 6 halves, negative 3. Okay, at 1, 5, we get 1 minus 2 by 5, 10, negative 9. Okay, in this case, x is 10 thirds minus 2 times this y, that gives us minus 11. Alright, we need to be in the realm of thirds. 10 thirds minus 33 thirds, negative 23 thirds. Alright, now let's look these numbers over. We're looking for a minimum. What about this situation here? Negative 9 thirds, also known as negative 27 thirds, indicates that right here is our conclusion. Okay, so a minimum value of z equaling negative 9 occurs at x, y equaling 1, 5. There's our conclusive statement there. Okay, something we need to do here, and that's that we should check out the calculation of the region R. A lot went into that. There was 4 lines graphed, and then a side of the line was chosen, so many sources of error. Let's at least give it some sort of check. So check of R calculation. What we could do is we can find a point that's surely in this graph of R. Okay, so it's ½ centimeter per unit. Okay, 1.5 centimeters is like sort of right in the middle of R, so this is definitely in our graphing region. That would be 3 for an x coordinate, and for a corresponding y coordinate, kind of getting something that is most definitely in R, not as a result of a slight graphing error of a line. And it looks like 1.5 centimeters is pretty much right in the middle of R here, when x is about 3. Okay, so 3, 3 is surely in our R here. We can say is an element of R, like that. And now, if that's the case, what's supposed to happen? That means that this point, when substituted into each of the defining inequalities, must make them true. So let's get started on that. First inequality there, 3 by 3 for x minus 14, 3 for y. How about that being greater than or equal to negative 67? Okay, let's see, we get 9 minusing 42. Let's see, that's a negative 33. How about that, less than or equal to negative 67? Think of the real number line. Negative 33 is to the left of negative 67. True. Okay, second inequality. That will be 27 times 3 plus 4 by 3 less than or equal to 112. That's the statement that results. Okay, 3 by 27, 81, plus 4 by 3, plus 12, 81, 91, 93. Okay, that's true. Alright, start kind of bulleting these, keep things organized. Let's go to third inequality. X plus 2y, so 3 plus 2 times 3. How about that being greater than or equal to 6? 3 and 6 is 9, greater than or equal to 6. Okay, true. Alright, last inequality to be checking. 11 times 3 for x, plus 2 times 3 for y. How about that, greater than or equal to 21? There's 33, there's 6 more, that's 39, greater than or equal to 21. That's true. Okay, so this gives us a check on R. The region R appears at least to be correctly graphed, so that's in order. Part C says, using calculator and or computer apps, illustrate this problem graphically. Alright, we're sitting here with the TI Nspire CX calculator, and because this has 3D graphing capabilities, which is something we need right now, and so I've got this graphing page here opened up. want to view 3D graphing. Okay, and here we can put in our formula here. It says we have x minus 2y, so x minus 2y, and enter. Okay, let's take a look at this. We were expecting to see a plane because we have a function z, a function of x, y, so it's in 3 space, and it's linear, which means we know it's going to be a plane, and we can kind of spin this around a bit to get a good look at it. Now let's see, I want to kind of capture an image here that I need to then draw the domain on and then project up and down onto this plane to actually get the graph of our function whose minimum value we have calculated here. So I think I'll let the xy axis come in front here. Okay, this might be a pretty good view right here. I think I will go ahead and capture this image here. Okay, now I will now start adding some domain sketching and project onto the surface to more fully show what this question is about graphically. So now it's off to Windows Paint. Okay, after adding on some details in using the Microsoft Paint program, got this. Here is the graph of the function z equals x minus 2y. That's a plane just by itself. Alright, that was from the TI Nspire calculator. I removed the box actually from that, and that was just to keep from having so many details on this graph. Next, the region R, the domain, is sketched here in the XY plane. That's a quadrilateral that we developed manually. After you have the quadrilateral, you then project either up or down, as the case demands, to get the actual graph of the function, which is here in the green, f. Okay, so the actual function we've studied in this question is f, and it is a quadrilateral in 3 space. That's what it is. Now, you noticed that on 3 of the vertices the value came out negative and 1 was positive. Well, why is that? Because this quadrilateral is actually slicing through the xy plane. So we found we had up here, there's that 1 positive value of z came from this point here, and the other 3 are all below the xy plane, here, here, and here. The lowest point of all. What we were seeking, the value, the z coordinate of this point down here, and this is the lowest point on the graph. Another thing to kind of help understand this graph is that this plane actually slices through the xy plane along this line. You can figure out this line easily because by going to the z equals x minus 2y, well, when is this slicing through the xy plane? Slicing through the xy plane means z is equal to 0. So you set z equal to 0 here, and that gives you 0 equals x minus 2y, or in other words, y equals 1/2 x. Thus the equation labeling this red line where the plane slices through the xy plane, and have that as to help visualize this graph as well. It's kind of nice to see that this minimum point on the graph here matches with our algebraic result that we achieved in part B. So everything kind of comes together here, and it's nice to have a visualization of what this problem is all about. Okay.